Welcome back, my dear students. In the last video, we have discussed about the chemical shift in NMR spectroscopy. That is, we studied that every proton in a organic compound is not in the same chemical environment, and the chemically different protons resonate at a different frequency or at a different field strength, and that is due to the shielding or deshielding effect by the electrons nearby the proton. Therefore, the chemical environment has a pronounced effect on the spectra of NMR spectroscopy. Okay, and we have studied about chemical shift and its representation, delta and delta scale and tau scale, etc. Now we are going to discuss about the another interesting thing in NMR spectroscopy, that is spin-spin coupling. Okay, if we consider, for an example, a spectra of 1-bromopropane CH3 CH2 CH2Br. According to we have studied earlier, there are three chemically distinct protons here. That is, this proton, this CH2 is a distinct proton, this CH2 is another distinct proton, and this CH3. Three types of proton, that is CH3, CH2, CH2Br. Three types of protons are present here, and therefore all are chemically different. This CH3 is different from this CH2, which is different from this CH2. For example, this CH2 is attached to Br, this CH2 attached to CH2 and CH3, this CH2, so this CH3 only to CH2. That means they are in different chemical environment. So we expect, according to we have studied about chemical shift, three distinctive lines in NMR spectroscopy. Here also we get three lines, 1, 2, 3. But an interesting thing here is the TMS. This is a delta value 0, and that is the value of TMS. That will be here. That is not shown in this picture. Okay, here we look at here. That is this line. This is line 4. I think this is the line for the CS3 group, and this CS3 group is split into a quartet. That is 1, 2, 3, 4 lines are here. Okay, split into a quartet. And this is the line for CS2, this CS2, CS2Br, CS2 attached to Br. And that is split into 3, 1, 2, 3. And the middle CS2 group split into a, that is into a 6 lines. A sextet of lines is obtained here. Okay, and that is the thing. It is due to the phenomenon called the spin-spin splitting. Okay, we will explain this more details. That is actually the spin-spin splitting is the indirect interaction. It is the indirect interaction between the spins of neighboring magnetic nuclei that is transmitted through the intervening bonding electrons is called the spin-spin splitting. The indirect interaction between the spins of the neighboring magnetic nuclei, that is neighboring proton, that is transmitted to the intervening electrons. That is, if you consider there is a proton attached to a CS proton attached to an electron. Electron is here, and another CH is here. This each electron has a spin. Hydrogen also has a spin. So each acts as a tiny bar magnet. Therefore, the spin of the proton is the spin of the electron is affected by the spin of this proton, and this spin of electron which is affected by this proton transmitted as an influence the spin of the electron in the another CS group, and that spin affect the spin of this hydrogen. That means indirectly the spin of hydrogen, this hydrogen is affected, is transmitted to spin of this neighboring hydrogen through the intervening electron. That is, spin of this proton affect this electron, that affect this electron, which affect this proton. Okay, in this way the proton spin is affected by neighboring proton through the intervening electron, and that is called spin-spin splitting. And this spin-spin splitting causes the splitting of lines into multiplets. Okay, that is if you consider, for example, CH3, CS2Br, this split, the field of line of CS2 group is affected by this neighboring CS3 group. That is, a line for CS2 group is split into several lines or split into several lines due to this neighboring CS3 group. Okay, actually this line for CS2 group is split into 4. Okay, that we will explain later, more details. We got 3 hydrogens are here, therefore the CS2 line split into 4, and due to this CS2 group, the line of CS3 group split into 3 triplets. Okay, that will explain. The multiplicity of a given equivalent proton depend on the number of protons in the adjacent group. Okay, multiplicity of a given equivalent proton depends on, that is, the multiplicity of this CS2 group depends on the neighboring CS3 group, and multiplicity of this CS3 group depends on the neighboring CS2 group. So due to this interesting thing, we can find out, we can get an idea about the chemical environment of a particular proton, because the splitting of this proton is affected by the neighboring proton. Okay, neighboring environment can also studied by NMR spectra due to the spin-spin splitting. Okay, the general rules for spin-spin splitting is equivalent protons do not undergo observable splitting. For example, if we consider CH3 CH2Br, the splitting of these 3 hydrogen cannot affect themselves. That is, splitting of one of these hydrogen cannot be affected by hydrogens of this group. That is, equivalent hydrogen cannot split. Similarly, if we consider this compound CH2Br and CS2Br, the splitting of these 2 hydrogen cannot be affected by this CS2 because all these hydrogens are equivalent. So equivalent hydrogens cannot affect. Therefore, we can say hydrogens on the same carbon cannot undergo spin-spin splitting if they are equivalent. Okay, then next one important point is a signal in NMR for a set of equivalent proton split into n+1 component lines, where n is the number of equivalent protons in the adjacent set. That's very important rule. That is, for example, if we consider again this compound CH3 CH2 OH, ethanol. Therefore, the splitting of CS2, like a line of CS2 split into first we consider CS3. The splitting of CS3 proton, the line of CS3 proton split into 3, that is n+1. Here its neighboring proton is 2. Here n is the number of the equivalent proton adjacent to the set. Therefore, adjacent to the CS3 there are 2 hydrogen. Therefore, it split into 2+1. That is 3 lines. Okay. Similarly, this OH proton, the neighboring proton is CS2 again 2. It split into 3. Okay. Clear. This CS2 I will explain later. That is very important point. A signal in NMR for a set of equivalent protons split into n+1 component lines, where n is the number of equivalent proton. If there are 3 equivalent proton nearby, therefore this line split into 3+1 4. If there are 2 neighboring proton, is split into 2+1 3, like that. Okay. And that is third point. Suppose a set A of Na equivalent proton, and another set X having Nx equivalent proton, both spin couples with a particular set M of Nm equivalent proton, then the signal of M split into Na+1 into Nx+1. Leave it. Consider an example, very simple example. We already discussed CS3 CS2OH. That is, this CS2 proton spin couples with this CH3 and this OH. Okay, that is, there are 3 protons here and 1 proton here. Therefore, this line of CS2, the field of CS2 or the frequency of CS2 split into, according to this rule, Na+1 into Nx+1, that is 3+1 into 1 plus 1, that is 4 into 2, that is it split into 8. That is why in the first thing here we get 3 plus, here we can see that this CS3 6 lines, because due to this line here 3, this CS3 3 plus 1 into 2 plus 1, that is 4 into 3, that is 12 lines. Okay. Some mistake is there. I think it is okay, I will explain later. I think here 12 lines is to be obtained. Okay. Yes, next thing is the total area of signal does not change due to splitting of the multiplets. Okay, total area does not change. However, the theoretical relative line intensities of multiplets are symmetrical about the midpoint and will be proportional to the coefficient of the binomial expansion 1 plus x raised to n, where n is the number of equivalent proton that interact with the proton under consideration. That is the splitting. We know that we said that the equivalent protons split the lines into several multiplets, and the intensity of these multiplets is actually equal to coefficient of the binomial expansion 1 plus x raised to x raised to 1. That is actually the Pascal's triangle. We already studied Pascal's triangle. That is, if there are 0, if n is equal to 0, then we get only one line with intensity 1. If the n is equal to 1, then the line split into 2. Line split into 2, that is, we get a doublet with line intensities 1:1. If n is equal to 3, we get 3 lines, that is, we get a triplet with intensity 1:2:1, like that. If n is equal to 4, we get 5 lines. Sorry, if n is equal to 2, 1:2:1. If n is equal to 3, we get 4 lines, 1:3:3:1. Like that, using this Pascal triangle, we can predict the line intensities. That is, due to spin-spin splitting, the line split into multiplets, and the intensity of this multiplet depends on the coefficients of the binomial expansion 1 plus x raised to n. That is shown by this Pascal triangle. It's very easy to study. You already know. I think you know about this. Okay, and fifth point, the midpoint of the multiplet represents the resonance position of the group and gives the chemical shift. Okay, the midpoint of the multiplet represents the resonance position and gives the chemical shift. So chemical shift delta value is measured if there is a multiplet, that is already we have discussed here. Okay, actually this center point is the chemical shift. Chemical shift value is obtained from this midpoint. Okay, that is we have already told, and that is the main condition for the general rules for the spin-spin splitting. More details about this we will discuss in the next video. Okay, thank you.